Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support. This is a bit unusual for the podcast, but I wanted to dedicate this episode to my mother, Lorrie Michele Parson. It is with great sadness that I must tell you she passed away earlier this month after a brief but courageous battle with lung cancer. If my mom had grown up today, I'm confident that she would have been a scientist or engineer. She had an analytical mind, a great sense for design, and paid attention to detail like no other. Yet my mom embraced being different in her own way and blazed a unique path for herself. For example, in 1992, just over 25 years ago, she started a travel agency at a time when the internet was beginning to completely disrupt the travel industry. She saw the impending changes, the writing on the wall, and wisely chose to focus on vacations rather than airline tickets, which dominated the time of most other travel agents. None of her early business colleagues, who nearly unanimously warned her against this strategy, are still in business today. Mom's founding of a travel agency was also no accident. She had a lifelong love of travel and exploring the beautiful diversity of our world. She visited 115 countries in her lifetime, all of which are documented with pushpins on a giant wall map in her basement. Not a day goes by when I don't try to embrace Mom's "it's okay to be different" attitude, whether at home or at work. It's also important for me to note that for the majority of my life, my mom was my number one cheerleader. While she would joke that she stopped being able to understand what I was working on sometime in middle school, she always fought fiercely for me and supported me in my endeavors. I wouldn't be the person, husband, father, researcher, or teacher I am today if she had not been in my life. Words cannot express my gratitude. And now, as Mom would say, get on with it already.
So what NASA Langley Research Center was doing was putting each one of their specimens into an electron beam lithography system and processing them for 57 hours. And so a friend of mine at NASA Langley was complaining about this to me one day, and we figured out that we should be able to just put the pattern that he cares about into a flexible polymer stamp, put some ink on it, ship it to him. 15 minutes later, he's processed his specimen with these stamps.
That's Andrew Cannon, talking about microspeckle stamping. Andrew started 1900 engineering to commercialize this microcontact printing-based technology that can map strain in high-performance materials. His technology helps engineers understand when and how parts fatigue, knowledge that is critically important for industries ranging from aviation and aerospace to construction and automotive. We talk about how 1900 engineering's technology works and how the stamps are fabricated, but also discuss a number of the long-standing challenges to precision patterning at the micrometer and nanometer length scale. At the end, Andrew talks about some of the pros and cons of starting and working at a small company. I think you're really going to enjoy this show, both Andrew's story and the way he tells it. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. I'm talking to Andrew Cannon. So Andrew is, among other things, the editor of Nanovation. And he was one of the first people that reached out to me after I had released an episode or two. He had somehow stumbled on the podcast, started listening, reached out and said he had enjoyed it. And I was thrilled to have someone who said they were listening. And then time passed. The last, as people who listen would know, the last year has been a little bit slower. At least the first half of the year was very slow in terms of release of episodes. And then Andrew followed up and said, hey, so I haven't seen a podcast in a while. And I said, yeah, this and that, whatever, life gets in the way, have to get money to do research, et cetera. And, more or less we had a brief conversation, and it came out that you said, I love podcasts. I enjoyed this podcast, and if there was a way for me to contribute, that would be great. Yeah. And I was like, yes. and I think we've built a nice collaboration.
Yeah, I think so too. Yeah, it's been a lot of fun for me also. Right when you first released the first couple episodes, I remember reaching out because I'd been thinking it would be really nice to have a podcast like this. And I was really happy to see that someone bothered to do it, because I know it takes a lot of time and energy. I think at the time I compared it to the Econ Talk podcast that Russ Roberts does out of Stanford University.
And he is far more articulate than I will have to say that.
I don't know. I think that you underestimate yourself, actually. And also, I think I've told you before, he has something like 20 years on you, so it's...
I've actually wondered. I've never looked up how old he is, but he's older than. Okay.
Yeah, oh, definitely. So anyhow, yeah, I was really happy to see that we've got a science and technology nanotech version of Econ Talk where you're allowing people to have a ladder to climb up into the ivory tower, take a peek, understand the sort of conversations that scientists and engineers have, and hopefully for the public to get to know people like us a little better. So yeah, I was really happy that I was able to contribute to the podcast, as I think that we're doing something really important.
And I think we're like-minded both in our interest in this aspect of science and technology, but then also in what podcasting is, right, and what it enables. I think there's something that both of us really appreciate in that.
Yeah, definitely. I think that we both appreciated the student from India who contacted you over email, right, and said something about he found this sort of discussion really important, especially, I think he said especially for people in countries like India.
Right. In that case, without having as much access to the kinds of journal articles and things that we kind of take for granted at Georgia Tech, that particular person was thankful that we provided this service.
Yeah, I think that there's value in it that way, and I think there's also value in putting some more real faces and real voices to people that do scientific research. So I think that most people get their scientific research news through the popular media, probably mainly just through headlines. And sometimes that's good, and then other times it's just sort of confusing to people because there's not so much context into what it is the researchers are actually doing. I think the more that we can do to explain ourselves in real, clear, digestible terms, that's going to be good for society as a whole, and also good for us as the researchers.
Yeah, and I think the audio extended format of a podcast allows us to also talk about the nuance and the uncertainty that is inherent in any aspect of science and engineering.
Absolutely.
Right, and I think that gets missed in some of these short news articles where it sounds like everything's hunky-dory. There was a breakthrough from this one group this one time, and that you miss a lot of the broader context, as you were saying, and how things fit together and where there are still questions, etc.
Oh, yeah, absolutely. Yeah, so in order to tell a neat, tidy story, you've got to leave out the fact that just because the basic science got settled, that doesn't mean that we're just 2 years away from being able to buy this product at Walmart for some reasonable price, right?
Oh, for
there's
sure.
There's a lot of work that has to be done to get anything just from I discovered a new thing to it's actually usable for anyone that can walk into a store and buy something. And one way that I've heard it described is that we're playing baseball, we're not throwing darts. You look at professional dart throwers, they're incredibly accurate. Professional baseball players, just because they swing and miss at a ball, that doesn't mean they're terrible batters, right? So if they get a hit 30% of the time, that's a great professional baseball player. And that's sort of the realm that we're in. It's high risk, high reward sort of work.
Right. That's an interesting analogy. I hadn't heard it before, but it makes sense. So let's set the stage here, because I wanted to have you on, and in fact, I asked you to come on the podcast over a year ago, because when you contacted me, I knew what your background was in, and that was in patterning of surfaces.
Yeah.
And so we want to talk about that a bit today. And why don't you start by talking a bit about your background and your trajectory, and then we can talk about 1900s engineering and microspeckling.
So I got into nano and microfabrication in grad school when I went to Georgia Tech. I was in Bill King's lab, and at the time, Bill King's lab was split into two different camps. So there was this one camp that made and used these atomic force microscopes that are these very small diving boards with the sharp tips on them that can probe surfaces and can be heated up to be the world's smallest heat source to affect surfaces. And there was another camp that focused on micromolding, micro-embossing of polymers, because the idea is that so many things around us that we use every day are molded, because molding is a manufacturing process that is high throughput and low cost.
So first of all, tell us what molding is.
So molding is shaping a material that is formable in a controlled way. So in front of me, I have my laptop, and there are plastic components which were molded. So the plastic probably came in small pellet forms. They were heated up, they were melted, they were pressed into a form that created its shape, and then cooled down so that they wouldn't flow anymore. They'd solidify and then popped out of the mold. And the whole thing happened pretty quickly enough for that part to be very cheap. Lots of plastic parts around you were molded, probably in an injection mold, maybe in a compression mold. This isn't just a process for plastic. You can also shape metals in a similar way, and glass too. So it's a manufacturing process that is used to make things quickly and inexpensively. And that also can be used to make parts with structures that are very, very small, all the way down to, I believe the smallest I've seen has been 2 nanometers, when people have molded single carbon nanotubes using silicone rubber. So that was the camp that I was in Bill King's lab at Georgia Tech.
So this is a tiny bit of a tangent, but then something like 3D printing, which I'm sure a lot of listeners have heard about in the popular media as of late, is a way to kind of directly create that structure versus having to put something into a form that is the inverse, basically, of that shape, right?
That's right. So 3D printing is a great technology in terms of being able to draw something in 3D and then have a printer spit out plastic. What is a disadvantage for 3D printing is that you really are confined to parts that have features that are larger than what you can get with molding. So I mentioned the smallest thing I've ever seen molded is 2 nanometers. I don't know about you, Mike, but the smallest thing that I've seen commercially available 3D printed are parts that are something like 0.5 millimeter wide, with features that are 0.5 millimeter wide. Is that about right from what you've seen?
I feel like I've seen smaller things from research labs.
Okay.
Definitely not the kind of tens of nanometers for sure. I feel like I've seen people down at tens of microns.
Okay.
But don't quote me on that.
Okay. And we use 3D printing every now and then for the work that we do, when we're going to use a mold where that portion of the mold doesn't need microscopic textures, but then we do some micromachining to a different part of the mold. So we do use that technology of 3D printing, and it is handy, but you're not able to get to nearly the small scale of structures that you can get if you're molding a plastic. And what's interesting, it's not like you're confined to just 1 or 2 super fancy plastics. You can use all sorts of different cheap plastics that are made for cheap molded everyday products. Things like polyethylene, polypropylene, silicone rubber, urethane rubber, this is a technique that can create microscopic features and nanoscopic features on a wide variety of polymers if you just mold it in the right way. So, right, I got my start in Bill King's lab doing graduate research there, focusing on micromolding. And we started working on the science of hydrophobicity, which is where you're creating very small spikes in a surface so that the surface tension of liquids, usually water, the surface tension is a force that actually holds the bulk of the liquid on top of those small spikes that you're creating. So some people create those small spikes using etching processes in silicon, and that works great. It's just that it's expensive to etch silicon every time you want to make something interesting. And so the way that we made that more accessible to real-world applications is to use these molding processes to create the very small spikes that were good for suspending liquids on top due to surface tension.
So then, when you talk about hydrophobicity, there's, I guess when I think of it from a naive perspective, there's Rain-X. That I can put on my windshield, right? Mm-hmm. And then there's like the lotus leaf, which people always hold up as this kind of the epitome of maybe you would call it super hydrophobicity, where it's not even that it rolls off like water would with Rain-X on a windshield. It stays a ball of liquid sitting on the leaf or on some surface you've engineered to do the same thing.
Yes. Okay. Yeah, the lotus leaf is amazing. Here's a fun story for you. So I was in Hawaii for my honeymoon, and my wife and I, we were on the island of Kauai, and we found this Hindu monastery that did these open tours every Friday. So we went and we did the tour, and this Hindu monk was showing us around, and they have these amazing botanical gardens, right? So he showed off the lotus leaf, of course, and so he splashed it with mud, and the mud fell off of it perfectly, and everyone was amazed. It's just an amazing thing to see. And he said, I was reading on Wikipedia last night that there's actually some scientists that are studying this for engineering purposes. And my wife laughed, and he looked at her, like wondering why she was laughing at him. And she said, well, he's one of those scientists. And so, then the monk turns to me and he's like, well, can you tell us a few things about this? And so I did. I told them about being able to create these man-made versions of the lotus leaf. After the official tour ended and we were all just sort of walking back, the monk came over to me and said, what else can you tell me? Because I do these tours every week and I just run out of stuff to say.
So what'd you tell him? I'm curious.
Well, I just told him more about the surface tension of the liquid, and it works better for water than it does for oil. And if you pour oil on it, it's not going to come off so easily. It's going to soak in. And then we talked over email a little bit as well. So I got back and sent him some more information. I sent him a couple of scientific papers, and I didn't hear back right away, and I assumed that, maybe it was a little boring or something. But a week later, he responded and he said, thank you. I've shared this with the other monks around here. We really appreciate just getting a different perspective. And I appreciate getting their different perspective.
That's the best thing about traveling, just hands down, in my opinion. And one of my favorite things about doing science is that it's just an international endeavor. And so you're learning from people who have all sorts of different backgrounds and perspectives.
Oh, yeah. Yeah.
I've been interested or just fascinated lately, and it's partially because I have colleagues here in the department who work on making paper super hydrophobic, super oleophobic, which means very oil repelling, and they even make papers that both repel water and oil.
Yeah.
And I love it for that fact, and also just that they can take something that's as disordered as a paper surface. This is very different than the kind of engineered surfaces that people started with when they tried to mimic the lotus leaf and that, say, were etched in a silicon wafer or something like that. But it's just fantastic that you could put this on paper and have oil beat up and water beat up because of the microscopic structural and the chemical details of that surface.
Yes, it's amazing.
It's crazy. So, okay, let's go forward then. That's where you got your start. And then, so how did you kind of meander to where you are now?
So what happened is we worked on creating these hydrophobic structures in polymers, like silicone rubber. And then my committee member, Sam Graham at Georgia Tech, he gave me some castable ceramic and asked me to figure out how to mold microstructures into it. So we figured that out, and we figured out how to do it on curved surfaces using the flexibility of the silicone rubber. So then Michelin Tire Company actually came to Georgia Tech, and for one of their processes in molding tires, they used rubber molds that made ceramic molds that then made aluminum molds, and then the aluminum they pressed into tires.
Oh, wow.
Right. So it was just incredible that just by happenstance, we had been sort of marching slowly along that trajectory. And one of the things they were interested in was making water repellent tires. They could mold these structures into the tires. There's lots of things that you can do with surfaces if you have the right structures in the tire. Friction control is another thing. And so they were interested in for a lot of reasons. How do we mold controlled microscopic textures into our tires? So when they saw that we'd already done the polymer side into the ceramic side, they were very excited, and so they funded my PhD work. We then actually moved up to the University of Illinois. Bill King transferred up there. I came along with him and finished up the doctoral work at Illinois, where we got the metal side. It was a lot of fun, actually, because I would receive some of the Michelin Tire Company mold positives at Illinois. I would integrate these microscopic surfaces into the parts of the molds that they cared about. And then I would fly back down to Greenville, South Carolina, where they have their North American Research Center, and worked with their mold shop guys to process those things into the next step of the polymer side, the next step of the ceramic side, and then the metal molds. And the basic idea, the larger idea for our research group was industrially useful processes that enable micromolding real-world products. And just in that example, it would happen to be tires, but it can be other things because lots of things are molded. And it turns out that tire rubber is an amazing material. So it's great at not only molding, but demolding without ripping apart very small-scale structures. So what happened is when we got the processing working well, Illinois filed some patent applications based on the work. Michelin licensed those patent applications, and then one of the Michelin guys actually started up a company based off of that work, and I moved down to South Carolina to work with that company. So that was something like 7 years ago. We did a bunch of interesting work, met a lot of interesting people, and one of those people is the VP of Engineering. He and I split off together to start up 1900 Engineering. So for 1900 Engineering, we do a lot of micromolding of specialty scientific components and tools for researchers to use. And most of the time, that's all about allowing researchers to avoid using lithography, especially electron beam lithography, because it's so expensive and time consuming. And then sometimes it's to enable these researchers to get the benefits of these controlled microstructured surfaces on curved surfaces rather than something that looks like a silicon wafer, which most of our cleanroom equipment is set up to process.
And so explain to me how microspeckling fits into this. It sounds like it might be a sub-aspect of what 1900 Engineering does.
Yeah, so it is. There are a number of researchers who want to get the benefits of electron beam lithography without incurring the costs, right? So they love to be able to design their patterns. They love to get repeatable results in their micro and nano patterns, but they hate spending so much time waiting on the lithography system to process their specimens. Some of our clients have spent 57 hours on one specimen to get 1 square centimeter of area patterned. And then the cost is high as well. Not only the capital cost, but then just the the hourly use cost can be very high. So when we're able to provide to them flexible polymer stamps that have the designed pattern that they want, and they can use stamp number 1, 2, 3, 4, and get the same pattern over and over again, they're getting those benefits that they liked in lithography, but they're spending like 15 minutes using one stamp rather than 57 hours.
Okay, so let me stop you for a second. So this sounds a lot to me like what I usually think of nano imprint like this. Can you kind of compare and contrast this with nano imprint? Maybe it is nano imprint.
It's a version of nano imprint. Some people might call it microcontact printing or microtransfer printing.
So describe how that works then. So there's some layer. I mean, go ahead and explain exactly how this would work.
So the way it works for us is that we create one master mold one time, and we might use a process like electron beam lithography, where you put a electron sensitive resist on a silicon wafer. So you zap that electron sensitive polymer resist with an electron beam in a specific pattern. And so now you have a mold because you've created this pattern on this polymer. So now you can use this mold and cast all sorts of polymers to it and demold those and use them for whatever you like. So what we use it for is we apply these very thin inks to the polymer replicates from that mold. And then now we have a stamp that has ink on it. It's pre-inked stamp.
Oh, I see. So it's like a return address thing. it's ready to go. I buy it from you, and I literally don't need to do anything. I just stamp my surface.
Yeah. I mean, really, some of our clients, they just use a hot plate and a timer. Yeah, they really don't need a clean room environment.
So is each stamp used once then?
Usually.
I see.
Yeah, usually a stamp is used once. But right, so when they receive the stamp from us, it's ready to go. They can open the box, heat up their hot plate, put their specimen on their hot plate, and then put the stamp on that hot plate for 1 minute. And then peel it off, and then they've got their designed, repeatable pattern on their specimen that they can use for their processes. So this phrase of micro speckles, that might be new to you. I'm guessing you've not necessarily heard about speckles before. Is that right?
I feel like I know what a speckle is in the abstract, but no, I haven't heard of microspeckling.
Yeah, until just a few years ago, I hadn't heard people talk about this before. So there's this technique in material science that's widely used. It's called digital image correlation. The deal is that, especially for aerospace applications, if you're going to use any new material, you really want to make sure you understand how that material behaves. So there can be 10 or 15 year approval timelines for these materials. One of the ways that material scientists verify that a material can be used in a new aerospace application is by using this technique called digital image correlation, which allows them to get very high resolution strain maps of a surface and to understand how that material behaves in fatigue, for crack propagation, for all sorts of different material science testing. If you've gone through a material science course in undergrad, you might have come away with the idea that when you pull on a material and you put it under, say, a 1% strain, that the entire material is experiencing a uniform strain. But if you look really closely at a surface, then you can see that it's very non-uniform, right? Mm-hmm. So some parts of the material are getting much higher strains than others. And even though you're putting the whole thing in tension, some parts can actually experience compression. So what you can do is you can put a field of dots all over this surface, and then you can put that surface under a microscope, and you can pull on it and watch how those dots spread apart from each other.
I see.
Yeah, so in the material science world, those dots are called speckles, and some folks will talk about decorating a surface with speckles, where we might just say that you're micropatterning a surface.
And you then watch how are you probing the changes to the speckle pattern?
the same algorithm that is tracking how your optical mouse moves around on a surface is the algorithm that is tracking how all these dots are moving relative to each other.
So it's optical based.
Yeah. Well,
Okay.
yes. It is. That's right. So it's digital image correlation. So you're using images that.
Okay.
Right. So the images that the computer is actually processing to understand how the dots have shifted, twisted, moved from frame to frame.
And it's a full 2D image and not just like a laser being scattered.
Right. Yeah,
Okay.
This method is a full 2D image. There's actually 3D versions of this.
Okay.
And so, it's interesting. Some people will just put down a perfect grid of dots and get some results. But the problem is, you can imagine if you've got a perfect grid, if you shift that thing by half a unit cell left, well, the computer has no idea comparing image 1 to 2 if you've gone left or right. So there's specific designs that actually make some of these spectral patterns much higher quality than others. So our collaborators at NASA Langley Research Center have spent a lot of time designing spectral patterns that have extremely low noise. And so when you go and you've done your testing that's taken a lot of time and energy, you don't get caught in this trap of, well, gee, if the spectral pattern had just been better, then we'd have better results. These guys have designed some very low noise spectral patterns that lead to better results. So what NASA Langley Research Center was doing was putting each one of their specimens into an electron beam lithography system and processing them for 57 hours to get 1 square centimeter of usable area. And so a friend of mine at NASA Langley was complaining about this to me one day, and we figured out that we should be able to just put the pattern that he cares about into a flexible polymer stamp, put some ink on it, ship it to him, and then, 15 minutes later, he's processed his specimen with these stamps.
So this makes me think of a follow-up question here. So I can certainly see how this is valuable in the kind of R&D phase. And then it makes me think, well, that's clear. Is this the kind of thing, given the low-cost, highly repeatable nature of it, that you could then extend to parts on operating aircraft? Where you could, I don't know, you could monitor as a function of time of a 30-year life of a 737 critical parts and making sure that they are still mechanically robust or whatever.
So what people are looking at is embedding these acoustic particles so that if a crack is propagating through one of these critical components and then it hits a particle that is different than the surrounding metal, then it essentially says ouch, right? It sends out an acoustic signal, and there's some microphones that are listening for the signal all the time.
Oh, really? Oh, it's a continuous monitoring thing.
Yep.
I would have thought it was sending in sound waves that propagate differently, and you can measure the differences, in January, February, and March.
No, this is, the idea is that it actually says ouch at a specific time, and you hear it say ouch. We haven't talked about putting these fields of spectrals on the parts that can be checked from time to time. As I understand it, the aerospace industry usually does this by just replacing parts every 10 years, whether it looks like it needs replacing or not.
Yeah, right.
I mean, and that's not to knock them. That's just a safety decision that they've made. When an airplane falls out of the sky, it's a really big deal. And so they just made that decision to just replace the parts and be done with it. But right now we are focusing in the R&D phase. That's right. So it's high temperature materials like nickel alloys that people are interested in adding to rockets that are going to experience high temperatures. Right now, this month, the really interesting thing that we're working on is a weld band in an oxygen tank that NASA has recently made some changes to. So if you've seen the movie Apollo 13 or just familiar with that mission got all messed up because an oxygen tank exploded. And so every time NASA makes a change to how they construct one of these tanks, they test it to make sure that change is going to be a good change. So that weld band is not flat, and that weld band is something like an inch wide. The scientists at NASA are not certain what exact portion of the weld band they're going to want to zoom in and investigate at high resolution. So what we've done is pretty interesting. So imagine you're looking at a QR code, because a lot of these spectral patterns look something like a QR code.
Mm-hmm.
You see blocks of black next to a white background. Now, you zoom into those black blocks, and you notice actually they're not individual blocks. They're actually collections of very small black blocks that are just so densely packed together, they appear from afar to be one big black block.
Got it.
Then you see on the white, it's actually not white, it's a light gray because it's a low density collection of these very small black dots.
Mm-hmm.
And so what we've done is we've created stamps that have this multi-scale patterning to them, sent them up to NASA, and NASA is applying them to this 1-inch wide weld band, and they're going to run their digital image correlation tests with a zoom out view at first, and then as they see, oh, that area there looks interesting, let's, hit the enhance button, enhance, right?
Right, yeah.
Zoom in and get the very high resolution version of that test. But if they had just started off with the really high res stuff, they might be running many more tests, not knowing exactly where the interesting areas are going to be.
So each of these larger squares they repeat.
Yes.
So but you're looking for big squares that seem to have an issue, and then you zoom into those squares and look more closely.
Yes. So going back to your question about it being an optical method, I should say it's actually a image-based method. So you can get those images through optical means. You can also get those images through electron microscopes. In addition to this digital image correlation test in an electron microscope, there's also a common test called electron backscatter diffraction, and that gives you local strain information and also dislocation information, and it's complementary to the digital image correlation data, but it's a little different. So up until now, these tests have been mutually exclusive. If you have a specimen that you want to run digital image correlation testing to, you have to put speckles on it, and those speckles prohibit the use of the electron backscatter diffraction testing. What we've done is come up with an ink that we apply to these stamps. The ink goes on about 10 nanometers thick, and the ink is dark enough to do these digital image correlation tests, which typically run at 5 kilovolts. But it's light enough when you crank up the voltage for the electron backscatter diffraction tests at 20 kilovolts. The ink is light enough so that you can see straight through it and do these electron backscatter diffraction tests. It's sort of a disappearing, reappearing ink.
That's very cool, the whole thing. I want to pick your brain a little bit as well, as someone who works broadly in the area of nano and micro patterning. And I look at it as there's lots of things that can be done. We have some success at the micro scale. We have some success at the nanoscale. One of the areas where we seem to continue to struggle is with nanoscale patterns at high rates. And I just wonder what your thoughts are about that. I mean, maybe there's something I don't know about and I'm a complete idiot, and that there's something obvious that's going to be able to do nanoscale patterning at high throughput. But I struggle to see it, and I just want to get your perspective on that as someone who's immersed in this on a daily basis.
Yeah, so you're not an idiot, that's for sure. It's a struggle. But I think there's a lot of high throughput manufacturing processes that we already have. And I think that it would be smart to focus on those existing high throughput processes. So there's plenty of people that actually do talk about micromolding and nanomolding, like you mentioned, the nano imprint lithography. There's some other processes that are continual, such as calendar rolling, right? So if you can get these structures into rolls and then just roll, say, sheets of polymer, then you can make a lot of square feet of nano-textured material quickly. Also, there's processes such as extrusion. Extrusion is not something that you usually see talked about in nano-manufacturing literature, but it's an interesting one. If you can just create extrusion dies or extrusion mandrels, just things that shape the outside or the inside of extruded products, then you micro or nanotexture those, then you have a continuous process that can create products that are sold every day. So in case you're not familiar with extrusion, you think about the way spaghetti gets made, right? So you have a round die and you press some moldable material through that round die, and then you get a round shaped thing on the other side. So, I think that if we start with thinking about processes that are already spitting out miles of products per day, and we just think about how do we get nanotextures into those processes, that'll get us there faster than if we try to think about it from the ground up, or if we start getting too fancy with new processes that we haven't stood the test of time.
If I understood what you said, you more or less are going to do something like you do with the stamps, but you're going to put it on a roll so that you can just continuously pull a substrate or roll over a substrate.
Yeah. So you can attach it directly to rollers. You can micro machine rollers. That probably is going to get into your nano desires. But so nickel electroforming is a pretty commonly used way to make some metal nanotextured stamps, right? So you can attach those directly to rollers, or you can essentially make a belt out of those and sort of feed the belt through. Huh. You can also, one technique that we've used in the past is to place the material that you want to get the nanotextures into on top of one of these flat nickel tools, and then just feed that combination through a roller, which works very fast and provides a lot of pressure that molds the material right into the shape of the nickel tool.
Huh. And those features can be nanoscale?
Yeah, they can.
Interesting.
Now, none of this is a slam dunk, though, right? I think that it's still a difficult thing to pull off, but in an encouraging way, I believe that if you just look at CDs and DVDs, I believe that DVDs have molded bumps in them that are something like 500 nanometers wide. Do you know if that's right?
It's certainly nanoscale.
Yeah, and they're molded, so, and they're cheap,
right?
So
when they're pressed, which is molding, right?
Yeah.
So there's that scale. There's kind of lab scale. There's, let's call it CD or DVD scale, and then there's the real large scale stuff, right? If we took all the areas of all the DVDs, I know we're not making DVDs anymore, but at the height of DVD manufacturing, if we took all that area, it probably wouldn't be that large ultimately.
So you're looking for something like, we're going to cover half the rooftops in America with solar something that is nanotextured, and something on that scale, I guess.
Yeah, I think that's an interesting scale. I'm a chemical engineer, so
yeah.
I like big, gigantic reactors, and so just really large processes. I have a good friend who used to work at DuPont, and I might have told this story on the podcast before, but DuPont made Tyvek. Right now, DuPont is owned by Dow. It's now Dow DuPont. But Tyvek is this polyethylene moisture barrier, the white wrap that you see on homes being constructed. And to give people a sense for how fast that's manufactured, it's in linear speed, it's 8 meters a second, which to me is mind-boggling.
Right.
But that's the kind of speed you need for something like what you were just mentioning, which is cover
a bunch of roofs or cover half the state of Arizona with some kind of advanced nano-textured solar cell.
Right.
If you need the highly resolved pattern. And so that to me is really interesting and challenging. I sounds like we don't have a solution at that scale, and that we could very well get there. I tend to fundamentally start to wonder, okay, as I start to pull substrates at a rate that looks like even a meter a second, right? All sorts of shear forces and other things, let's just take a roller, if you had a roller with a stamp on it, start to become really problematic the faster you pull the substrate or faster you roll the roll.
Yeah.
And I've also learned never to say engineers and scientists can't figure something out, because they always seem to. But that seems to me to be, at those enormous scales, quite challenging.
Yeah, I think it is very challenging. I think it's not obvious how to get there right now. But I wouldn't be surprised if in the next 20 years there is a great solution and it feels a little obvious in hindsight.
Right. It always seems to. Not always, but it very frequently seems to.
Yeah. Well, and I also think that if there's just applications where a small-scale structure that doesn't have to be perfect and the pattern itself has some durability to it so that if you're missing things here and there, it's okay. I think that those applications are something that we could have some success in too at these large scales.
Right, certainly. That eventually, and I think any process at that kind of scale will have imperfections.
Yeah.
Right. That's the mantra of at least the chemical engineer, and it's certainly the mantra of lots of other disciplines, even if they don't say it the same way as a chemie says it. But the idea at large scale that you will have mixtures of products that will have to be purified and cleaned up, so to speak, is just, it's what you have, and it's always what you have. And so thinking about not only can you get close to those features, but can you design such that you're robust to errors and even come up with ways to eliminate errors that have happened at those large scales. I think there's just an exciting area to think about doing science or engineering in. But you also bring up a good point, I think, that you need a technology pull, right? It would be helpful to have a really clear need in some space, maybe a high-value need, that would drive a ton of work in that area.
Yeah, we usually talk about market pull versus technology push.
Sorry, I butchered that. That's exactly right. What he said is what I meant to say.
No, absolutely. And that goes for not just this area, but life in general. That doing what the market demands is going to be the smart way to go. I mean, you and I could draw up something that we think is just genius and convince ourselves that the technology would solve all the problems. But if we're the only ones that agree with ourselves, it's not very useful.
Right. Okay, so we have just a few minutes left, and there's one aspect of your work that I wanted to touch on and have you chat about for a few minutes, and that's working at a small company like 1900 Engineering. Maybe you could talk a bit about your size and what attracts you to it, and then also what are the challenges of working at a small company like that?
So at a small company, you have a good deal of creative control. If there's a method that I feel passionate about using for a particular project, I can go after that. I don't have to be constrained by some sort of long-standing protocol that our company has been using for a long time. If there's a particular customer that has a compelling need that I find compelling personally, I can go after satisfying that need. There's not layers of bureaucracy to deal with.
Mm-hmm.
Now, on some of the disadvantages, there's also not lots of people that are specialized in things that you might be accustomed to having those specializations. So, for example, like I'm the person that deals with a fair amount of HR things. So things like what health insurance are we going to choose? Things like how do we set up our retirement accounts? Those are things that I am not specialized in figuring out, but it becomes a worthwhile thing to get right. There's also this aspect of, I'm a a technical person, have a PhD, I am not inherently skilled at figuring out contracts that some of our clients send over to us. And so my initial inclination is just I'm not too excited about going over the new contract that came along with the purchase order, right? I just want to get to work.
Right.
And I just don't want to deal with inter-organizational bureaucracy, but it's important to do. And so I've just got to get over it, or I'll lean on my colleagues here, and we'll all just figure out what it is that needs to get done in terms of contracts, HR, whatever it is that none of us are necessarily specialized to take care of.
It's a bit like graduate school in a way, but you didn't have to do those things in graduate school, but you did have to figure out a lot of stuff along the way that no one really could help you with.
Oh, yeah. Well, and I'm sure also being a professor, I mean, I'm sure that I've had professors in the past joke about things that they didn't teach in professor school about how to teach your students, right? I mean, it's not like you've probably never had a in-depth course on how to run a classroom. I imagine you sort of just jumped into it your first year at Georgia Tech.
Yeah, there's definitely no required courses, right? There's help available, right? At Georgia Tech, we have the Center for Teaching and Learning, and they have a number of opportunities that you can avail yourself of, but not everyone does, that's for sure. And at some level, a lot of it is just got to get in the trenches like some types of engineering, or maybe all of engineering, and just do it and learn from doing. So that's a lot of it. Yeah, there's definitely no professor school. I used to wonder when I was a student, because man, and I'm sure some people listening have felt this, that what is wrong with my professor? Like, when did they become so kind of not lackadaisical, but absent-minded, right? There's this stereotype about professors of being absent-minded, and some are not, and some are more than others. But I always wondered, what was it? Was it something inherent about people who went into the profession? Was there some door you walk through, that once you walk through the door, you got these magical powers of... And I think a lot of professions, people would say they have similar experiences, but this lots of stuff going on all the time, and so you end up, dropping the ball more than you'd like, and it mortifies me. I'm not personally somebody who ever feels comfortable dropping the ball or forgetting about something, especially if I've promised something to somebody. But man, I feel like I'm doing it a bit more these days than I ever have in the past.
Well, but I think that it's so rewarding when you've got the creative control that you have at a small company that I imagine you have as a professor.
Right.
And it's rewarding when the projects work out and the work that you're trying so hard to achieve with people that you care about, that things come together and you get the results that you've been striving for the past year. And it makes sense, and everyone's learned something new and useful.
I completely agree. And on that note, I will say thank you so much for taking a few minutes coming on the podcast, and also thank you for doing all the great work editing the podcast.
No problem. Thank you.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.